Now let's see how can we find out the traffic capacity of different gradings. First of all, we will see what is an ideal grading. An ideal grading would be such a grading or such a system in which uh, uh, each trunk has equal load. For example, we have a traffic of A lengths and we have n trunks. Then the occupancy of each trunk would be A divided by n. You can see at this page. It is assumed that each trunk being busy in an is an independent random event, and if we find out the probability of having all the k trunks being busy is b, which is the grade, which is also called the grade of service, or the probability of all the k trunks being busy, and it would be equal to a over n, which is the occupancy of one trunk. We multiplied with the occupancy of the second trunk, which is again a by n, then the third trunk, which is occupancy of the third trunk, which is again a by n, up till the kth trunk, which is also a over n. So the total probability of all the k trunks being busy is a over n raised to power k. That is a over n of which is the occupancy of each trunk is multiplied with the occupancy of each other trunk, and for k different trunks the value b is equal to a over n raised to power k. So the number of trunks required to carry A lengths with the grade of service of B is therefore given by n is equal to A into B raised to power minus 1 over k. This equation is simply derived from this earlier equation that we talked about, which is B is equal to A over n raised to power k. This is also called the Erlang's ideal grading formula and gives a linear relationship between the traffic and the number of trunks. Number of trunks is n, traffic is a. So there is a linear relationship because B is given as a certain B is given by the regulatory authority, which is normally given as 0.01 for the trunks. So this gives a linear relationship between n and a. Practical gradings do not satisfy this condition of Erlang's ideal grading. That is not an ideal situation. What happens? The relationship between traffic capacity A and the number of trunks is not linear for a given value of grade of service B. An approximate curve of A against n can therefore be derived from Erlang's full availability theory of n being less than or equal to k. If n is less than or equal to k, and extended as a straight line for n is greater than or equal to k. So A would be equal to ak plus n minus k into b raised to power 1 over k. We are supposing that the number of trunks n is greater than the availability k. How would we find out the value of traffic handled in this situation or traffic carried in this situation? It would consist of two parts. The first part is the traffic carried by the number of trunks which is equal to the availability, which is k, and it is called AK, which is the traffic carried by a full availability group of k trunks with a grade of service of P. The second part, which is n minus k into b raised to power 1 over k, which we have derived from our earlier equation here, is due to the trunks that are in addition to the number of to the availability number. The availability number was k, and the additional number is n minus k. N minus k, it is multiplied by b raised to power 1 over k. Here a is taken here and b raised to minus 1 over k is taken on the other side, and it becomes n into b raised to power 1 over k instead of minus 1 over k, which was here. So it is a is equal to n into b raised to power 1 over k. And that relationship is used over here. So this total amount of traffic in Erlang's is found out to be ak plus n minus k into b raised to power 1 over k. Now we elaborate it from an example, which is example 5.2. We have to find out the traffic capacity of two groups, two group grading shown in figure 5.4 if the required grade of service is 0.01. We have to find out the traffic capacity of the two group grading of this case, figure 5.4. Here k is equal to 10, which is the availability, and from equation 4.1 ak is equal to 4.5 Erlang's. How did we find that out? Let's go to table 4.1. See the column for 0.01 grade of service, and for the number of trunks equal to 10, we have 4.5 Erlang's of traffic. We have 4.5 Erlang's of traffic. From equation 5.8, that is the last equation that we have derived, a is equal to ak plus n minus k into b raised to 1 over k. We put this value over here. A is equal to 4.k, because this particular table is for full availability groups. This is for full availability groups. So the value AK comes from this table. So the additional trunks would carry some additional traffic, and what would it be? N minus k into b raised to power 1 over k. N was 16 minus, here you can see here n is 16, just a second. Here n is 16. The total number of trunks here is 16. Minus 10, which was k, into b, which was 0.01, raised to power 1 over k. K was 10, 1 over k is 0.1, sorry. So 16 minus 10 is 6 into, if you find that value, it becomes 0.631 plus 4.5. You multiply it and add, we get 8.3 Erlang's. We note that in table 4.1 shows that full availability group of 16 trunks can handle 8.9 Erlang's with 0.01 grade of service. Let's check it out. With 16 trunks, how much traffic is handled? With 16, we can handle 8.9 Erlang's of traffic. Right? With 16, we can handle, but that would be the case of full availability groups. But since we have divided the groups, we have two groups. It's not a single group having access to all the 16 trunks. So that is the difference. So if it had been a single group with full availability, it could have handled 8.9 earnings. But in this case, while we have been using two groups and the availability is not full, the availability is limited, even then we can handle 8.3 earnings of traffic. And that is only possible due to the fact that we have been using the grading. How? Which grading? This much of grading. We have commoned these four trunks together. Now let's see what does this curve show us. This curve shows us the relationship between the traffic that can be handled by the number of trunks. If we have the full availability system, then lesser number of trunks would handle larger amounts of traffic. As the availability reduces, the number of trunks required to handle such traffic would increase. See, these are the curves for different values of availability. Here it is full availability, then a little bit less of availability, which is 40, then 20, then 10, then 5. As the availability is reduced, the number of trunks required increases to handle the same amount of traffic which is given in earnings. Now let's move on to the switching systems. As we have already discussed earlier, the switching systems are made in different stages. They use different stages. We can have a two-stage network, or three-stage network, or four-stage network, or five-stage network. And let's see what are the advantages of such a network. You can see this figure 5.11. This is a two-stage switching network. It has totally capital N incoming trunks and capital N outgoing trunks. And there are G number of primary switches and G number of secondary switches. And each of these primary switches has small n number of inlets. And each of these secondary switches has n number of outlets. Now what happens is that all the outlets of this particular switch, this one switch, they go to all the switches on the secondary level. They have one connection to each of the secondary switch. This is the first secondary switch, then second, third, fourth, fifth. This is the gth secondary switch. And for each secondary switch, this primary switch has one connection, one link. This is one link. The second link goes to the second switch, third link goes to the third switch, fourth and fifth, and gth outlet goes to the gth switch of the secondary level. Now, what would be G? G is the number of primary switches. How can we find it out? We divide by the total number of incoming trunks, which was capital N, by small n, which is the number of inlets of one single switch. Capital N over small n gives us the value G. Similar is the case of the number of secondary switches. We divide the total number of outgoing trunks, which is capital N, by the value small n, which is the number of outlets of one of these switches. When we divide this value capital N over small n, we get the value G, which is the number of secondary switches. The total number of cross points in the network is equal to the number of switches multiplied by the cross points per switch. So here what would happen is, what is the total number of switches? Here the total number of switches is G, and here the total number of switches is also G. So the total number of switches would be 2G. And what is the number of cross points per switch? N into G, and here G into N, still same. So we can say 2G, which is the total number of switches, we multiply it with the number of cross points in one switch, which is G into N. So C2 is equal to 2G into N. How does that come out? Because the total number of switches is, the total number of cross points in a switch is G into N. And G into N, from this equation we get equal to small g into small n is equal to capital N. So we can replace that G into N by capital N, right? So C2, C means the cross points, and 2 means two-stage network. The number of cross points for a two-stage network is equal to 2G into Gn. So we, if we replace Gn with capital N, we have 2G into capital N. We can also replace this G, and we can write it as 2 into N square over N. N square over N, because G is equal to capital N over N. So capital N and this N would become N square divided by N, and G would be removed. Since there is one link from each primary switch to each secondary switch, the number of links is equal to the number of primary switches multiplied by number of secondary switches. That is, the number of links is G square. This is G is the number of primary switches and G is the number of secondary switches. So the number of links in between would be this G multiplied by this G. That would be G square. And what is G here? G is equal to capital N over small n, and we get capital N over small n whole square, which is G square. So the number of cross points thus varies as 1 over n, but the number of links varies as 1 over n square. If n is made very large to reduce the number of cross points, there will be too few links to carry the traffic. Let the number of links be equal to the number of incoming and outgoing trunks, a reasonable choice since each set of trunks carries the same total traffic. Then G square would be equal to capital N. Taking this case, we can substitute in the last equation 5.10. In this equation, what would happen? G square N would be equal to under root of capital N. Thus the total number of cross points from equation 5.9, from 5.9, 2 into n square over small n, we put the value of small n equal to under root n, we get C2, which is the cross points, number of cross points in its two-stage network, to be equal to 2 into n raised to power 3 by 2.